Hello everyone, we are Group 4.
I'm Shi.
My name is Jun.
I'm Brian,
I'm Suchi. I'm Vanessa.
and today we are going to present about DC generator.
Hello everyone. So today we are going to talk about the working principle of DC generator. So before I start explaining the working principle of DC generator, I would like to introduce two important concepts that you all need to understand, which are Faraday's law and Lenz's law. So according to Faraday's law, it states that a changing magnetic flux through a loop of wire will induce electromotive force, EMF. Whereas for Lenz's law, it states that the induced magnetic field will be in a direction that opposes the initial magnetic field that it creates. So here we have a DC generator, and now I'm going to explain the function of each component here. So the function of carbon brushes is to maintain contact with commutator and allow the current flow without tangling the wire. And here, the commutator is to allow the current reverse in direction after a 180-degree rotation. And now we have permanent magnet, which provide a magnetic field from north to south. And here, lastly, we have a wire coil which allows the induced current to flow when the DC generator start working. So how does it work? So if I were to rotate the coil here in the clockwise direction, what will happen to the magnetic flux? It will increase from this direction, from north to south in this direction. So according to Lenz's law, it said that the induced magnetic field will be in a direction that opposes the initial magnetic field that it creates. So now we have to create a magnetic field in this direction to oppose the increase in magnetic field here. So now according to the right hand palm rule, the direction of the magnetic field produced is in this direction to the left. And as I rotate the coil in the clockwise direction, at this point the force is acting outwards. So here, the direction of my thumb will symbolize the direction of the induced current flow. So here, the induced current will flow from A to B and continue by B to C and C to D. So now, at this point, there will be no induced current. The question is, why? This is because now the direction of the force acting on this coil is parallel to the direction of the magnetic field provided by the magnet. So now we have this picture. Does it look really familiar to all of you? Actually, it's quite similar to what I have shown you just now. Just that now the position of D is here and A is here. Everything is like inverted already. So now let's do some revision. So as the coil continues to rotate, the change in magnetic flux here will increase from north to south in the right, A to the right position. So according to Lenz's law, it says that the induced magnetic field will be in the direction that opposes the initial magnetic field that it creates. So we will need a magnetic field, we will need to create a magnetic field here to oppose the change in magnetic field here in this direction. So now, do after me. So we have a direction of magnetic field in this direction to the left, and now at this point, the direction of force is acting outwards. So now, tell me, what's the direction of the induced current? It's from D to C in this direction. As you can see, your own right hand or either my own right hand, it shows this. So if this process were to keep on repeating, we can actually produce a lot of energy by converting mechanical energy to electrical energy. So that's how a DC generator works, and that's it.
Now we're going to look at how to draw a magnetic flux graph and an EMF graph for a DC generator. What we have here is just the different stages of a clockwise rotating coil within a magnetic field that's pointing in this direction. Let's take a look at the flux graph first. All we need to do to obtain the values is to look at the normal of the coil and where it points in relation to the direction of the magnetic field. Okay, so starting from position A, the normal of the coil points in this direction. That's the same direction as our magnetic field. At this point of time, we have the most magnetic field lines passing through the coil, which means that we have a maximum flux. So now I just want you to imagine the coil rotating to position B. The number of field lines that passes through the coil would be decreasing, right? In fact, at position B itself, the normal of the coil is pointing downwards. No magnetic field lines would be passing through the coil. So our flux is 0 here. Position C looks almost the same as it did in position A. They have the same amount of magnetic field lines passing through. But the normal of the coil here is pointing that way. That's opposite the direction of the magnetic field. So this means it's a minimum point on the flux graph. Position D has the normal of the coil pointing upwards, and just as in position B, no magnetic field lines are passing through at this point. So then it just returns back to position A. Now we can plot our EMF graph. The EMF produced depends on the rate of change of the magnetic flux. But hang on, this is a DC generator. So as we discussed earlier in the working principle, the DC generator has a split ring commutator, which allows the brushes to maintain their polarity, making the output positive. Therefore, our EMF graph should be completely positive too. We can say that the EMF graph is basically the modulus gradient graph of the flux graph that we have here. We know that the maximum and minimum points of the flux graph have a gradient of 0. So we can easily plot these points onto our EMF graph. And there's a maximum negative gradient here, and a maximum positive gradient here. Though it really doesn't matter if it's negative or positive, since they all end up a maximum on the EMF graph anyways. And if you notice, the DC generator is also arranged in such a way that it changes from one split ring to the other while the induced EMF is 0.
I'm going to talk about mathematical equation related to DC generator. P represents the number of poles of the generator. Phi is the flux produced by each pole in Tesla meter square or WB. Z is the total number of conductors in armature. N is the speed of armature in revolution per minute. A is the number of parallel paths in which conductors are distributed. The total flux produced by all the poles can be calculated by the number of poles of the generator times the flux produced by each pole. The time taken to complete one revolution can be calculated by 60 divided by the speed of armature. According to Faraday's law of induction, the induced EMF of the armature conductor is equal to the rate of cutting the flux, which is the rate of change of flux produced by each pole, and can be calculated by the total flux divided by the time taken. The induced EMF of one conductor can be calculated by the total flux produced by all the poles divided by the time taken to complete one revolution. There are multiple parallel paths and each have a conductor. The induced EMF of one conductor is from here to here. The EMF induced in each parallel path is the same, and it is calculated by the total number of conductors in armature divided by the number of parallel paths in which conductors are distributed. And these are the conductors across which EMF is induced. So the total number of conductors are distributed in parallel paths. Effectively, Z over A conductors need to be multiplied with EMF induced in one conductor to get the induced EMF of DC generator. Therefore, the average induced EMF across each parallel path can be calculated by induced EMF of one conductor times Z over A. For a given machine, the number of poles and the number of conductors per parallel path are constant. N is the speed in revolution per second. The average induced EMF E is directly proportional to the flux produced by each pole, and the speed of armature in revolution per second, or is also directly proportional to the flux produced and the speed of armature in revolution per minute. Therefore, the average induced EMF is directly proportional to the flux produced by each pole and the speed of armature. There are also some question and answer for DC generator. What are the advantages of parallel operation of generators? And the answers are continuity of service and efficiency. So the next question is the resistance of armature winding depends on the length of conductor, cross-sectional area of the conductor, and the number of conductor. Copper brushes in DC machine are used where low voltage and high current are involved.
Good afternoon, my name is Jun and today I will have a short explanation on the EMF produced by DC generator. So let's have a basic background about the DC generator. An electromagnet is a temporary magnet. The magnetic field only exists when an electric current is flowing. Any electric current produces a magnetic field, but the field near an ordinary straight conductor is rarely strong enough to be of practical use. A strong field can be produced if a wire is wrapped around a soft iron core and a current is passed through the wire. The strength of the electromagnet depends on how many coils you wrap around and how high the voltage is. Moving on, the electromotive force produced by more coil DC generator. As the number of coils are increased and the magnetic field will become stronger. This is due to every coil has its own magnetic field, thus the more coils that are present means that there are more magnetic field lines. This then makes the electromagnet stronger. The stronger the electromagnet, the stronger the induced electromotive force. So, in conclusion, the increase in the amount of loops of coils will increase the magnetic field. The bigger the magnetic field means that there will be a bigger change in magnetic field, causing a larger induction of electromotive force. The more coils you have in your DC generator will increase the output of electromotive force. Thank you.
Lastly, one of the modifications done towards a DC generator is an inverter. An inverter generator creates AC power through a two-step process. In the first step, it generates DC power, and by using a microprocessor controlled inverter, it converts it to an AC power. The generation of DC begins as soon as the engine begins to turn. As the engine increases in speed, the DC voltage rises, but as the load increases, the voltage will fall. The microprocessor controlling the inverter compensates by sensing the AC output voltage of the generator and adjusts the speed to keep the voltage at a consistent level. This saves fuel since the engine only turns as fast as necessary instead of at a constant high speed, creating wastage. As the demand increases, the microprocessor speeds up the engine and power production increases. However, the signal does not change. The result is a very clean and consistent AC signal no matter how much power is drawn up to the generator's capacity. A very simple electronic inverter can approximate an AC signal, but doesn't do it really well. But with a microprocessor, it does a much better job and the converted signal appears to be a near perfect AC current. This method of power production has several advantages. It directly or indirectly reduces losses. When the drop of a load is significant, it can maintain the lowest possible speed necessary to meet the demand without shutting off and restarting the generator as the load increases. This is cost effective, reducing losses and efficient because if you are shutting it off and restarting it, you are consuming more fuel and wasting more energy. During the periods of low demand, it is also quieter than a conventional generator as it is running at the lowest speed possible. Compared to a conventional generator, you are running at quite a high speed, like constant speed. And through that process, you are using less fuel and you're producing a clean power without compromising any constant flow of current to your appliances. That will be all for today. If there is any inquiry, please don't hesitate to ask later. Thank you for watching.